We're going to look at an example problem using angle of twist for statistically indeterminate torque-loaded members. This is a slightly more complicated problem that I would put on an exam. I can't even talk today. So the question asks us to determine the absolute max shear stress in a 36 steel shaft with diameter 60 millimeters, which is fixed at both ends. So right here we're fixed, and right here that probably means that we're just in between a wall. I first wrote down my equations, which I'll probably need, and my given data, which is just basically the diameter, which I rewrote as the radius. And we could use this information. We're given the material, and if we're given a table, we can use this information to find what G would be for this particular shaft. So I always start out by looking at the entire body and doing the sum of the moments. And anything, I just came up with my own convention in this case. Anything that's rotating in the direction of TA is going to be positive. So TB and TA are positive, and the 500 and 200 are negative. So I get a final equation of TA plus TB equals 700. Now we need to consider the fact that the ends of the shaft are fixed. That means that our total angle of twist from point A to point B is going to be 0. And we know that the total angle of twist from point A to point B is going to be the sum of the angle of twist from A to C, C to D, and D to B. So overall, I just wrote my equation angle of twist A to C plus C to D plus D to B. And that in total is going to be equal 0. So the angle of twist equation is TL over JG, and I wrote that for every single section that I will be needing. Then I pulled out a J over G because all three of them have it in the denominator, and if I multiply this over, JG just disappears and we're left with 0 equals all of this stuff right here. That means we don't need to calculate J, nor do we need to know G in this problem. So from that point on, I started to cut the sections at every single point to find out what the T is in every single section. So for the first section, I cut it somewhere around here, and I have a TA rotating that way. That means I need another moment in the opposite direction to balance it out, and it's going to be the same magnitude as TA. Now once again, if this is my positive x-axis, then if I use my right hand rule, this is going to be the direction in which my fingers curl, therefore TA is going to be positive. So TAC, or the torque for section AC, is going to be positive TA. Then I cut it in between CD, and here I have TA going this way, I have a TC which is 500 going the other way, and once again I'm going to just presume, here you have to make assumptions and just make sure that your signs are correct, that TA is bigger than TC. So what I'm going to end up needing is a torque going in this direction to combine with TC to balance out TA. So I end up with TA minus TC. That will give me the magnitude that I need. And because it's in this direction, it's going to be positive. So TCD, so the torque for section CD is going to be TA minus TC. And we said that TC is already given to us as 500. So TCD equals TA minus 500. For this last section, I end up cutting over here, and instead of working from this end all the way down to here, I just work from this end because it's way shorter. So TB is rotating this way. Our positive x-axis is off of the direction of where we cut. That means we need a TB pointing this way, and if we curl our fingers, the curl actually goes with this direction, so this is going to be turn out to be negative TB. So the torque for section DB is negative TB. Alright, so now we have our three sections with our three different torques in each section. So here I just rewrote them again. So I go back into the equation that I determined from angle of twist, and I just plug all of my my unknowns in there and the distances. So we're given the distances, that's the easy part. So for TAC, I plug in positive TA For TCD, I plug in TA minus 500, and for TDB, I plug in negative TB. So I end up with another equation which has two unknowns, which is perfect because now we have our original equation for the full body and we have a second one that has two unknowns. So what I end up doing is taking my second equation, plugging in for TB, so that way I get an equation all in terms of TA, and I solve for TA and I end up with 414.29 newtons. And then I go back in and just plug in for TA, and I find my TB, which is 285.71 newtons, which is perfect. So now I have my TA and my TB. So that's how I use the angle of twist equation to determine the two unknowns. Then I want to determine the absolute maximum shear stress. So I need to find which section has the maximum torque. So TAC we said was equal to TA. So that's 14.29. TCD was equal to TA minus 500. So I got that. And then TDB was equal to negative TB. So I got that. And obviously the biggest torque turns out to be in section TAC. So that's 414.29. And I'm going to plug that into my Tmax equation, which is TC over J. So for T, I plug in TAC, which is 414.29. For my C, that's the radius, which is 0.03 meters, and then I have to calculate J, where J is pi over 2c to the fourth, and C is our radius. So once I plug that in, I get this, and my tau max, or my absolute maximum shear stress, turns out to be 9.78 megapascals. This is a quite involved problem with many steps. I'll give you a few kind of like important things. It's just paying attention to detail. You need to make sure that whenever you cut, you're paying attention to sign convention and which direction your torques are actually going. You need to know where you need to cut. So that means in between every single point where there is a moment. You need to find the torques for every single section. So basically every point that you cut, you need to find the T. You need to be able to find your two unknowns. So in this case, they were our TA and our TB, which were at the fixed ends of the shaft. You need to understand where Tmax is, and then at the end, once you found Tmax, you can find the maximum shear stress using Tmax. So as long as you get used to all of the processes, knowing and understanding what's going on, the sign conventions, you should be in good shape. So make sure you understand this problem.